Welcome back. Welcome back to our new lecture regarding PV solar system design. During today's lecture, we are going to focus on the battery design. Battery is very, very important element when it comes to PV system. Also, if you go into details, into deep details when it comes to power system, you will see that the future, the advanced battery system with energy management and renewable energy play an important role in network stability. Let's start our lecture today. So today's lecture, as we discussed, it's our third lecture, and we are going to study the battery design for photovoltaic system. But in general, what's a battery? What's an energy storage? So during today's presentation, we're gonna speak about energy storage importance to PV system, utility grid, and network stability. We're gonna give a brief introduction regarding this element. Then we are going to talk about energy storage. We are going to focus on the battery. That's why we talk about batteries, history, and types. Terminal voltage and internal resistance. Like I said, we are going to focus on the battery system. When it comes to energy storage, charging and discharging requirement. It's very important to make sure that the charging and discharging happen to protect your battery system. Battery capacity, life, and depth of discharge. It will be covered part of our lecture today. We're going to do some calculation analysis and examples, equation to aid the designer when it comes to the above. How to design a battery bank to suit a certain activities. Battery sizing design. Safety precautions. Connection and commissioning. Maintenance, and then we're going to do a design example together. As you saw, we have a lot to cover. So maybe today, our lecture will be a little bit long, but hopefully at the end of the lecture, you will be able to choose the right battery storage, size it properly to suit your activities, and also do all the precautions, maintenance, operation requirement for your design system. Before we go into the system, why energy storage is important? We spoke in our first lecture that energy storage exists for a grid-connected system, feed in and feed out. Also, the energy storage exists for your grid-connected only, no injection as well, and also when it comes to the off-grid system. So when it comes to PV system, energy storage or the batteries is very important. It will help us. Actually, in this case, it's very important. On the previous one, when you have a power outage, when you have a system with a regular power outage country or an area, the battery is very important because this has a regular outage. I'll give you an example. A couple of countries in the Middle East, they have a regular power outage, as in Lebanon, Beirut, they have a regular power outage, so the battery storage is very important. Also, in the previous slide, before we go into a detailed design, I would like to ask ourselves multiple questions. What's an energy storage? What's an energy storage? Why energy storage is vital for numerous types of PV system? Why PV system with energy storage is vital for advanced grid stability? Let's first answer these three questions. When we answer these three questions, we will have some better understanding of the concept. What's an energy storage? Energy storage, what is it? It's a device. What's a water storage? It's a device that I can store water. When I have running water, I can store it for later deployment. What's a gas tank? It's a tank that stores the gas for later deployment. Energy storage, exactly the same. It's a device that will allow me to store the harvest electrical energy for deployment at later or at a desired later timing. Available energy storage system. I have a wide range of available. Some of them vary between sizes. Now, electrochemical. The electrochemical is the batteries and the fuel cell. This electrochemical, they call it electrochemical because when you have a connector load, the chemical reaction provide you with your electric requirements. Thermal storage. As an example for thermal storage is the brick storage heater. There is mechanical system to store energy, like a flywheel energy storage, which is, by the way, flywheel energy storage, along with solar system, could mitigate the dive into power output during this cloud. When the cloud is passing through, if you have any, you will have a drop into power output. This, if you have a flywheel energy as a mechanical device next to it, can also provide you with a stable power output. Electrical, like a capacitor. Chemical, like a biofuel or hydrogen storage. As you saw now, there is a large number of types, different types of energy storage. Today, in our lecture, we are going to talk about batteries. In a later stage, I'm planning a later stage after all the series to do one about the biofuel. Why energy storage? The second question, why energy storage is vital for numerous types of PVs. As we know, as we studied before in the past two lectures, the sunlight is a fuel, is the input fuel for the photovoltaic cell to produce electricity. The way day and night happened, the sunrise and sunset, winter, autumn, spring, and summer, the sunlight radiation changes when it comes to direction to the ground, incident to the ground, and also in magnitude of sun radiation. So therefore, the output of the PV panel changes throughout the day, and usually, depending on your orientation and tilt, the maximum power output is generated for a short period midday. This is a system, as an example. This is if you have an area, if you have any system facing south for the Middle East or the Gulf and tilted at an angle, certain angle, let's say 10, 20 degrees, refer to the lecture number 2 regarding all these details. This is the shape of our output. Don't worry about this, is an example. Could be 400 kilowatt, could be 400 watt. Now, as you can see, this is where the power is strong. As you can see, in a certain day, maybe between 9 and 3, 9 and 4. Okay, what will happen outside these hours? What will happen outside these hours? I have no power. Let's say my house, for example, my house, I have this portion of the generated energy. There is no use for it. There is no use for it. I have no load during this period. This energy has no load to go to. The MPPT, the maximum power point tracker algorithm inside the inverter, if there's no grid connection, if you don't send it to the grid, it will reduce the output of your system. So now your output of the system, your system output will go up like this. In here, it will drop down, in here, it goes down like this. Or what I can do is, I can use an energy storage where I can store this energy in a battery and then take it into heat. If I want, because in case I need here at 7 o'clock, I need the energy. and there is no electricity, or as we spoke before, in many countries, the electricity cost in this portion, the electricity cost during the energy cost during this is very expensive. So for me, if I want to maximize my energy, maximize my return on investment, I need to take this portion of energy and take it into heat. That way I can maximize my return on investment. This only can happen to shift the generated energy by providing some sort of storage system. The storage system will allow me to store this energy and then deploy it at a later stage with the aid of energy management. So that's why energy system, that's why energy storage is very, very important to PV system. The maximum output, it's not at the peak of your house demand, as we saw the other day. You remember the house demand? The house demand goes up, maybe the house demand goes up like this. So I need to shift this to heat. That's why the energy storage is very, very important. In countries where the peak hours exist in the late evening, early hours of the night, energy storage also is very, very important. Why PV system with energy storage is vital for advanced grid stability? Regarding this concept, we will do a complete session. But now, to show you why it's very important. Current data shows, all the data that we have available currently in the market shows that the peak hours of a house, of all the grid, exist during late hours of the evening, early hours of the night, when everyone comes back home. Give you an example. Let's say you work as a teacher. Comes back, goes back from 7 o'clock to 3:34, goes to work, come back home after 3:30. You and your kids start cooking. The kids turning everything on. If it's summer, they turn the air conditioner on. If it's winter, they might turn an electric heater on. So that's why all the electric peak demand exists during the late evening, which is about 4, 5, 6 o'clock, or early hour of the night, 7, 8 o'clock in the evening. During the grid peak hours, during these peak hours, as we saw, the electricity generated from the PV is very minimal. It's a very minimal. Actually, some of them don't exist. In winter, beyond 4 o'clock, you might not have any power output. The peak grid demand, during this peak demand, especially under heat conditions, when you have a heat conditions, when you have a heat wave, the capacity, the current carrying capacity of your transmission line will be reduced because of the heat, because of the resistance increased. So during these peak hours, your system, especially in summer, around 7 o'clock, 8 o'clock in the afternoon, your network could be at risk for overloading system. So what will happen is, I don't want to overload my system. So this could be the peak grid electric demand under certain conditions such as weather, heat wave, could impose risk at the electric grid. The PV system with energy storage can team up. So now, if I have a renewable energy with energy storage, I can team up with my system to offer me a better stable system. So now, after I provided all this information, I can say, hold on a second. Hold on, let's stop. As a utility, instead of I don't want to go and invest way more money, especially in the future. I can say, hold on a second, I have an energy storage somewhere. I can use it during these peak hours. What will happen is, when I use it during these peak hours, I will reduce the risk on my power system grid. That's why energy storage and photovoltaic system play an important role when it comes to network stability, grid network stability. Of course, the future advancement tools, we have a Industrial Revolution 4 is coming. We have machine learning, we have AI, advanced energy management is coming all the way from different providers, from different manufacturers like ABB, like Siemens, Schneider's. All this, I can use it because it has an advanced automation system to help me to manage my load distribution better. Now, let's have an example. I want to have an example. This is PV system output. This is my standard. I have a peak at 9 o'clock because some of the panels going toward the east, facing toward the east. This is my house. This is my house consumptions. As you can see, all this energy from that generated from the PV, all this energy from the PV, I have two choices. If I have a grid connected, I can inject to a grid, I can put it into the grid. However, during this period, the cost of electricity in many countries is very low. If I don't have a grid injection, what will happen is the MPPT, if I have no energy storage and no grid injection, my solar system output will be represented by the black one, like this. So now, this will be my electric generator. This will be lost. This will be cut by the maximum power point algorithm embedded inside your inverter. That's why, hey, I don't want to lose it. Also, I pay attention, hold on a second. I have this system in here. I have the system in here. All this power, I'm going to get it from the grid at a higher cost because located during the peak hours, I'm going to lose power from my generated solar system, and I have to pay extra power, extra money for the power that I am going to use. If I have a regular power outage, I could have a power outage in here. So what I do is I will store this into the battery and then take it and put it into here. From a grid perspective, what happened is, guys, look, from a grid perspective, this is what happened. Now, my grid, the power came from the grid all the way down to the house. Because I take it, it will become like this. Or maybe it's like that, depending on the energy. Can you see now what I've done? Is I flatten the peak. So imagine there's a million house, use the same concept for the utility, they no longer have a peak in the evening. They have almost flat because they use the stored energy during the peak hours. So as you can see from this example, that energy storage can increase the benefit to the house owners when it comes to PV solar system generation. Can further reduce the cost of their electricity bill, and also they can play an advanced role when it comes to peak, when it comes to surge in power requirement from the utility, can make sure it's stable. See, I can stable the system with the energy storage. That's for the 3 questions. That's the answer for our 3 questions that we asked. So as you can see now, these options, the battery, now I agree with everyone. We should agree now that energy storage is very important. Actually, it will form like a strong partner, like a strong bond with the PV solar system, the energy storage. I want to add one more element. We hear lately, electric car. What's an electric car? Electric car is made of electric motors, of course, another electronics, and an energy storage. In the future, they are expecting that under Industrial Revolution 4, in the usage or the deployment of electric vehicles is going to spike. So every single house will have a battery. Where it doesn't have to be house, every single work outside has a battery. where they can store this energy into already an existing car battery, and then there will be a mechanism, management, to feed from and to the grid from the electric cars. I just wanted to add this extra information. Now, as we discussed, this section, I can take this, put it into here, and as I showed you, it will flatten your curve. Now, it's worth noting, this is what I spoke to you, with the advanced in energy management tool, the introduction of machine learning capabilities. Utility can utilize the stored energy at houses with the consent of the owners to support the peak of the load. Utility, trust me, this is based on a previous experience. Utility, during this period, they suffer, especially if any fault happens. You know, during heat wave, if the temperature goes, for example, to a certain degree, they will stop all regular maintenance, all planned outages, they will cancel it. They will lose a lot of money because they don't want to incur any risk. They want to avoid any unwanted outage. With this ability, the utility can divert the energy to suit the desired stability. So now, machine learning, AI, automations, energy management, photovoltaic battery system will advance stability can be achieved when it comes to the grid. Batteries, that's where our core subject is. Batteries, it's not new. Early 1800. Volta, Mr. Volta, we're going to go through it now. In early, Mr. Volta used a chemical reaction. The Volta battery made of a zinc and a silver plate separated by an insulator, which is water and I think salt, acid. So Mr. Volta put a zinc and a silver plate. The plates are divided into positive and negative plates. So he put positive, negative plate into an insulator and then connected the load and the current start flowing through. It's important to differentiate between primary and secondary cell. When it comes to batteries, we need, as an engineer, as an educated personnel, or as a personnel, need to understand batteries. I have primary and secondary cell. Primary cell are the one that under reaction, one component will be destroyed and cannot be regenerated. So primary cell are not chargeable. You cannot recharge the primary cell. You can use, the one that you use into the battery that I have inside my device, maybe your remote. So this cannot be rechargeable. You cannot recharge the primary cell. The secondary cell, during the reaction, when it discharges, a chemical reaction will happen, which we will talk about it at later stage. Chemical reaction will happen when I start discharging the current from my battery. When I recharge it again, the chemical reaction can be reversed, the effect, the impact will be reversed to a certain degree. Nothing comes back 100%. To a certain degree, can be restored during the charging cycle. Therefore, the secondary cell are rechargeable. For the PV system, secondary cell are the required type of batteries. So for a solar system, we only use a secondary cell type batteries. Battery is secondary cell. Now, depending on the type, there's a plenty. If you search the internet, there's a large number of rechargeable batteries. The researchers and companies use different combinations when it comes to chemical reaction to design. Positive and negative plate material are defined depending, like I said, there's a plenty of them. For example, lead acid. The negative plate is made of lead and the positive plate is made of lead dioxide. So for this system here, I have negative plate made of lead only, positive made of lead dioxide, and the electrode is made of dilute sulfuric acid. So made of the sulfuric acid in between. And the voltage, the cell voltage, every cell voltage is 2.2 volt. Look at, for example, silver zinc batteries. Negative plate is made of zinc. The positive plate, not a place, plate, is made of sulfur oxide, and in between, the electrolyte is made of potassium hydroxide. The cell is 1.5 volt. See, each one of them is different. Every single lead acid or silver zinc. You see the difference? Now, each type has advantages and disadvantages. By the way, there's a few other types, but we're not going to go through them. This is an example to show you. Now, how do you make a battery? Depending on your batteries, as you can see, this is 2.2, this is 1.5. 12-volt batteries is made of multiple cell of this, or multiple cell of this, to make a 6-volt, a 12-volt, or 24-volt batteries. This is a battery, for example. This is your negative terminal. This is your positive terminal. You can see between them, you have every cell, you have a divider. You have positive. See, you can have the positive, the lead dioxide, and you have the negative, which is the lead. And you have the dilute in between them. See this? Dilute in between them. That's how the battery is being made. This battery, when you have charging and discharging, the chemical reaction can be reversed, as you will see soon. Now, for PV system design, the following elements are very important. Now, so far, we spoke about why battery is important. For what's a battery? Why battery is important for PV, for a grid, and then we spoke about different types of batteries. A little bit quick history about the battery system since Mr. Volta went early 1800, his discovery. Terminal voltage. I have a battery, guys. I have a battery system. I have a box. This is my batteries. I have in here 2 boxes, positive, negative. This is called, I'm going to call this V terminal, the terminal voltage at the battery system. The terminal voltage, which is impacted by the battery internal resistance. We just saw that the battery from the inside, it's made of lead dioxide, so it's made of material. Every single type of material, irrespective of what is it, timber, water, everything has a resistance. Some of them very low, some of them very high. So now, because I have an internal resistance, it's very important to find the relationship between the actual voltage of the battery and the internal resistance and the terminal voltage. Then, it's very important to study the charging cycle. As you will see soon, the battery can be damaged, heavily damaged, if I overcharge it, over-discharge, make it dry, 100%, and heat. That's why ventilation is very important. So charging and discharging cycles. I need to make sure I use the proper charging and discharging to make sure my battery lives longer. Its life cycle, how can I control the life cycle? Capacity and capability of the battery. These are very important for me when it comes to PV system. Let's go step one by one. Terminal voltage. I have, this is my battery. This is my battery system. I have the terminal of the battery where I connect my wires to. Guys, inside the battery has an internal resistance. This internal resistance, if I apply Ohm's law, if I have no load, that means the current in here is 0. This is I that goes into here. At no load, it's 0. Because I have no load. So therefore, V terminal will be equal to V. So this voltage will be exactly V. Because I have no voltage drop. I have I times R internal. I times I. I is 0. So this is 0. So that's why the voltage will be at the terminal. When I have a load current, I have V terminal. It's equal to the voltage minus IR. That's it. When I have a load, when I have this load, if I apply KVL. If I apply KVL or mesh analysis, I have the terminal voltage in here. I have V. V will be equal to this voltage will be equal to I times R internal. This voltage in here plus V terminal, which is the voltage across the terminal. So therefore, V terminal is equal to V minus IR internal. So it's very important. See, now, the terminal voltage is what my devices will read. You will see later on why this is very important concept. It's very important to understand the terminal voltage of my battery under different loading conditions. It's very, very important. So, I hope that's clear now, the relationship between the terminal voltage and the internal resistance, where Vt is the terminal voltage, I is the load current. Terminal voltage example. I have a 12-volt battery, has an internal resistance of 100 milliamp. I have the terminal voltage is 13 volt at no load. Calculate the terminal voltage when the output current is 20 amps. Okay. So guys, let's see now. What I have is, I have a battery. That's a voltage. I have an internal resistance. Then this is my terminal A and B. Then I connected a load. This is R load. This is R internal. This R internal is 0.1 ohm. The question is, this system at no load, V terminal at no load, it's equal to 13 volt. We know at no load, V terminal, it's equal to V. We just spoke about it. At no load. This terminal at no load, I have no R. So now, when I have a 20 amps, so this is fixed, the internal one. So now this I know it's a 13 volt. So now I have at 20 amp load, I have 13 volt, it's equal to 20 multiplied by 0.1 plus V terminal. So straight away, this will give me V, it's equal to 13 minus 2, it's equal to 11 volt. So straight away, my voltage at the terminal dropped. Straight away, as soon as I put the 20 amps load, this straight away dropped because of the internal resistance. It's very important to understand this concept, because you will see, how do you control, how do you assess your system capacity based on a voltage? How do you make sure that the system is not overcharged or over-discharged by reading the voltage? So that's why I need to be able to understand, what am I reading? Am I reading this one or am I reading this one? It's very important for me. I hope that's clear, guys. Charging cycle and battery voltage. Now let's look at the charging. We said one of the elements that kills our battery if I overcharge. That's it. This is an evidence. How do I charge my batteries? If you go to Ohm's law, this is my batteries. This is my internal. If I put Ohm's law state, if I have, this is my V of my battery. This is my R internal of my battery. This is my 2. This is another voltage, V, charging, V of the charge. What's Ohm's law state? What's Ohm's law state? If I put mesh analysis, what does it give me? It's give me minus VB plus IR internal plus V charge, it's equal to 0. That's mesh analysis. So basically, depend if this voltage is bigger than this voltage, the current will go this way. So therefore, I will be equal to VB minus V charge over RE. If the current is positive, that means my current is going up. It's going away from the battery voltage. If this voltage, let's put an example. Let's say this is 12, this is 14. So I would be equal to minus 2 divided by RE. So straight away from mesh analysis, I know, see, I took my mesh analysis, so I know the current is going backward. So I know the current is going backward. So now the current goes this way, and now it is charging. It is now charging the system. So for me to charge my battery, I need to use a higher voltage at the terminal of the battery for it to be charged. Now, how high should it be? How high should it be? Should it be, for example, 12 volt? I put a 100 volt to it, 50 volt to it? No, there's a certain limit. If I exceed it, I might damage it. Now, usually standard for a 12 volt battery, people use 14 volt, 13.8 volt. Now, the charging current reverse, as we spoke before, when you charge the system, it will reverse the chemical reaction and restore things to maybe, let's say, 99% or 98%, let's say 99.5%, depending on the system. So now, the charging current reverses the chemical impact on the material caused during the discharge cycle. That's why I reversed it. If I can reverse 100%, the battery will last forever. But it's not possible to reverse it. Now, if I use the wrong charging voltage and the wrong charging current, I'll fast track the life of my battery and will die early. Why? If the charging current is too high, the lead sulfate is quickly removed from the lead and lead dioxide surrounding. So if I put too much current, straight away I will try to push my chemical reaction to a limit that cause a blade corrosion and short circuit. See, it's very important. I should not put, how do I create high current? I created, could be a lot of different other things I can create by creating high voltage across its terminal. So this fast removal won't allow for the proper dissolving of the material. This causes blade corrosion and short circuit. Now, to avoid the corrosion and short circuit, there is a steps. Every single battery manufacturer provides you with the step required, or the voltage for each step. There is a 4-step, there's a 3-step for charging, and a 4th step to explain to you how to try to revive your battery. Before we go into it, I want to define C. If you have a battery, as the battery is defined, for example, 200 amp hour battery, C is 200 for this value. Now, I have nominal charge. I have a battery system. I have a stuff called nominal charge. The nominal charge is a higher voltage. Look, it's a nominal charge in the period where high charge rate is applied to ensure the battery is at 80 to 90% of its nominal capacity. So at the beginning, if the battery, for example, has 50%, I put a high charge to a limit. Now I have to stick within the manufacturer guidelines. So for example, if said for this type of battery, maximum 100 amps, my maximum goes 100 amps. I don't go beyond this. So I put high charge to reach it up to 80 to 90%. After I reach to 90%, I have a stage called absorption charge. In this section, lower current magnitude will be injected. Lower charge will be injected to take it from 90 to 100% capacity. And after this, I have the floating charge. The floating charge will be chosen to make sure that after the battery is 100%, the floating charge will make sure it will stay at this value, because there is a losses. There's nothing 100%. There's a losses, and the battery tend to automatically discharge itself slowly. So, three main components: nominal charge, where high charge rate is applied to reach 80 to 90%. Then the absorbing charge between 90 and 100, or 85 to 100. You will have the current, the charging current is reduced to ensure the battery now slowly. And then after it's fully charged, the floating charge, where it's a cycle, it's a voltage, put it into a calibration system. What's the equalization charge? Sometimes you need to revive, you need to shake it, the internal reaction. Sometimes you have, because of bad charging, when you have the cell, as you saw, the cells, they're not all of them. So when the charge goes through, not all the cells are discharged at the same rate. Not all the cells are charged at the same rate. So what I do is I apply a voltage to cause gassing. To go gassing is like, make it, shake it. Make all the reaction to go and move. So the material that hasn't been dissolved back to its original state, I use it. It's usually used when the battery capacity is deteriorating. So when I see that my battery is being burned like this, I will use this system, the equalization charge, to revamp it, to give it a kickstart. Is that clear? These are very important for you to understand. The reason why, when you become a PV solar system designer, when you choose a charger controller, by the way, most of the charger controllers have these titles. But when you choose the charger controller, you need to make sure that the charger controller is capable to charge your system without causing any damage, to extend its life. Is that clear? How do we determine the battery state of charge? The percentage of the battery terminal voltage in respect of the fully charged value. So, the battery, how do I know how much energy there is inside my battery? Let's say, for example, 100% is 14. 13.8, 13.5 volt could be 80%. Each battery will give you this chart. That's why the voltage terminal of my battery is very important. Very, very important to determine its capacity or its available capacity inside the battery. Look, this is an example of a 12-volt batteries. 12-volt battery, under 100%, the voltage is beyond 12.8. Could be 13, depending on each batteries. And at 50%, 12 volt. At 10%, 11.5 volt. And this is the equations. This is the equation is based on a previous research done at Western Sydney University in 2018. So guys, this is very important for me. Every battery data sheet, I get the data sheet and I get these values. When it's fully charged, what's the voltage? When it's 50% charged, what will be the voltage? And I set my inverter data to work between my desired limit. For example, do I want it to be 40%? I check what's the 40%. At 10%, I want to discharge 90% of the batteries. I can set at 11.5 volt. Depend on my desired parameters. Now, after we completed the charge, now we start talking about the discharge. Now I understand, based on when I measure the voltage across it, I know that this voltage, for example, has 80%, 90%. When it reaches to 90%, I will change into the absorption stage. Remember the absorption stage charge? See? Absorption charge. Because how do I know it's reached 90%? I know that it's reached 90% because of this graph. I set the values. I set the values inside the actual inverter or charger controller. I set the value to suit this element. Now, after I do all this, I understand now how to read the battery capacity based on its terminal voltage. I have to go to the discharge cycle. Why do I need the discharge cycle? Because I need to know how much I can take out of it and how should I take it. Remember the terminal voltage and the internal resistance. If I take the voltage, if I take higher current, my voltage terminal drop too fast. When the voltage terminal drop too fast, I have my charger controller setting will reach very fast. So I don't have much time. So I only can take out of this battery, run the battery for maybe half an hour, 1 hour. If I take my current slowly, I can extend the uses of this battery because of the voltage terminal and the internal resistance as we spoke. During the discharge cycle, the chemical reaction causes the current to flow in the closed loop. Depending on the battery capability, the discharge rate changes. Example. I have a 12-volt battery, 200 amp hour battery. We said when I have 200 amp hour, this I put a big C, designated to a big C for the capacity. So this is big C, simple. So what will happen now? Guys, look, I have an internal resistance. When my internal resistance is in here, I have, depending on the current that goes, this terminal voltage is being reduced as we saw. Which means for my charger controller, my control mechanism reads this voltage, doesn't read this voltage. That's why I need to make sure when I take higher current out, the time frame is lowered of the battery operations. This is an example. Voltage cutoff. This is my voltage cutoff. If I have a slow discharge, my battery will take longer to reach my cutoff voltage. Fast discharge, faster track because of the internal resistance to reach my voltage. The example, how long can the battery support a load current of 10 amps and another load current of 100 amps? How long? Now, in theory, if I have no internal resistance whatsoever, I have a 100 amp hour. I'm taking 10 amps out of it. So I can have C over 10. If I'm taking 10, which is give me about 10 hours. In theory, if I'm taking 100 amps out of it, I have C over 100. Which is equal to 1 hour. That's in theory. However, in reality, because I have an internal resistance, look, this is a real system, 1200 amps. When I take 1C, when I take 100 amps, look, let's get a different color. When I take 100 amps, this is 100 amps. Depending on what level I want to reach my voltage, look, for this 100 amps, for the voltage, if it was full, to reach 11, it's in here. It's about 25 minutes. If I want to put it at a 10 volt, to reach the 10 volt the battery, 30 minutes. When I use 10 amps, guys, see, it's just under 10 hours. So the lighter the current, the discharge current, I will be very close to the theory. The stronger the load current, I will be away. Instead of having 1 hour, I'm having 25 minutes or 30 minutes. And by the way, look, I'm discharging the battery almost 11 or 10. So I'm taking about 60% of its voltages. Is that clear? It's very important to take note of this. It's very important because some people say, hold on, I have a battery 100 amp. If I take 50 amps out of it, it lasts me for 2 hours. No, it will last you for 1 hour. You will take 50, so 0.5, 0.3, 0.5, so somewhere around here. So see, it's not gonna reach you 60, it's not gonna give you 2 hours. It will not give you 2 hours. It's very important. It's very important to pay attention to this element. So now, as a design, as a photovoltaic engineer design, you should ask your client, can you tell me what's your load? Can I see your load profile? Or you generate the load profile for your client to make sure that, for example, between 12 midday or between 5 p.m. and 6 p.m. or 12 and 1, this hour, I have a discharge current of a 50 amps. Can my battery stand this? Maybe no. It depends on your setting of the voltage. Now, this is my cycle. Battery life cycle. Before we go into the battery life cycle, I need to introduce stuff called depths of discharge. The depth of discharge is the percentage of the battery energy used in comparison to the battery full. So for example, do I need 30% depth of discharge? 30% depth discharge, that means I can only discharge 30% of its full capacity. If you have, for example, a battery has 100 kilowatt hour battery bank, 30% discharge, I only can use 30 kilowatt hour. If I have 50%, let's write it down. If, for example, I have 100 kilowatt hour total energy storage bank under 30% DOD, I only can use, is 30 kilowatt hours. Under 50% DOD, you only can use 50 kilowatt hour of its maximum capacity. For a lead acid, 50 to 60%. It's not recommended to go more because then it will be very hard for the battery during the recharge to fully recover. If you go beyond the 60%, you can go maybe up to 60%. You go beyond the 60%, in reality, in some way, you will impact the life of your battery. So it's recommended. Will this help me? Where this will help me? Perfect. I have a system. I have an energy bank. So someone have a battery. I have 10 battery, 12 volt, 100 amps. The capacity of them is 12 times 12 times 100, or 0.1. So 14.4 kilowatt hour. I have 14.4 kilowatt hour. Hold on a second. No, you don't. Your battery size is this, but you only can use 7 or 8 kilowatt hour. You know, that's why it's very important to know the DOD, the depth of discharge, because it will determine for you, it will explain how much you can take out of it. How will this help you to determine the battery life? For each battery, the DOD, the allowable maximum DOD is being provided to you. For example, deep cycle battery could allow up for 80% discharge, while other type of battery 20%. For example, car batteries, most likely they put it at a 20% because only for ignition and then you charge it. You know? So it depends on your battery. You need to read the data sheet. You need to understand how to read the data sheet. During our introduction session at a later stage, we will go through all this in detail. This is to give you information for you to comprehend, to study before our introduction session. The battery life cycle is measured. The battery is measured by life cycle. How many cycle can it last? For example, I have a battery will last at a 5,000 cycle under 30% DOD, could last at a 2,000 cycle. Look. Number of cycle, this one. Under 30% DOD, 1,200 cycle. Under 100% DOD, 200 cycle. 50% DOD, 450 cycle. What's a cycle? So every time you discharge up to 50% and you charge, that's one cycle. Every time you discharge 30% and then you charge it, that's one cycle. This will help me to properly size my battery system. Battery life cycle example. I have a 12 volt, 200 amp hour AGM battery. The life cycle, I need to have a life cycle of 500 cycles for an 80 DOD, 750 for 500, 1750 for 30% DOD. State the energy that can be delivered under each DOD system. Okay. The energy. Number one, the total power of my battery. It's equal to the voltage times the current. It's 12 times 200 amp hour, which is will give you 24, which is give you 12 times 2, 24 watt hour, or 2.4 kilowatt hour. That's a maximum power. That's my tank. Let's give you an example for water. If you have a water tank, 1,000 liters. However, you set your tap that can only 30% on the top. This is your tank. Your tank can 2,400 liters, for example. This is 30%. This is 50%. If I have a DOD at 30%, what I do is I go ahead and I install my tap in here. So when I open my tap, only this will go, which is represent 30%. If I want 50%, I put my tap in here. I will remove my tap, put it down. So now it will allow me to discharge this. So okay, I have 2,400 liters, 2,400 liters. But depend where I put my tap. For the battery, it's recommended for the lead acid to put it between 50 and 60. You cannot put it at a 10 or a 0. You will damage your battery. So now, under 80 DOD system, under DOD equal to 80%. Your power that you can take, P out of the battery, P out of the battery, it's equal to 0.8 times 2.4 kilowatt hour. For when you have a DOD of 50%, you have the P out of the battery. Maximum P out could be, if it's fully charged, it's equal to 0.5 times 2.4 kilowatt hour. If you have DOD of 30%, the P out will be equal to 0.3 times 2.4 kilowatt hour. Exactly, guys. So can you see now when I set the DOD of the system, how it will impact on, I could have a massive power bank, battery power bank. But because if I set my DOD, how do I set my DOD? Based on the voltage. On my charger, as soon the charger controller, the battery terminal reaches this volt, it will isolate. And that's how. Okay, I can in here take almost 2 kilowatt. In here I can take 1.2, in here 0.7 kilowatt hour. See the difference? It's very important to study the DOD system in details. If I don't study the DOD system in details, it will never allow me to complete a proper design. Battery sizing design and capacity. As we spoke, we just put this information now on the board that we just did. This is the equation that we just did. As an example, what's the capacity of the following battery? All we did now, 12 times 200, 6 times 400, 24 times 150. Same, we apply. 3B max, that's the maximum. Like I explained to you, consider your water tank. This is the maximum your water tank can take. But however, how much you can take out depends where you put the tap. Okay, I hope that's clear. So for this one, the answer will be 12 times 200 amp hour. For this one, will be 6 times 400 amp hours. For this one, will be 24 times 150 amp hours. The answer will be, the unit will be what? hours, watt hours, watt hours. This is volt, this is volt, this is volt. Is that clear, guys? So you guys can use this equation to calculate the maximum. Now, this is I want to design a battery system to support P kilowatt hour. So when I say design a battery system to support a consumption of P kilowatt hour per day, so every day, so clearly I need the P out, not the P battery, not the total size of the battery. I need how much I can take out is P kilowatt. To take into consideration the DOD, this equation will help you. This equation is represent. This is the required. This is the required output power from the battery. This is the nominal depth of discharge. This is the efficiency. That's the efficiency. This is the efficiency that I can take out. If I have a 90% efficiency. Now, this I want you to ignore this because this voltage is different. This is, don't worry about it for now. There's no need to use this one. Just stick to this because in here, there's an internal resistance you have to take into consideration. There's a lot of other things to take into considerations. What's V, what's AH, what's and so on. Is that clear? Now, for the batteries are very heavy if you want to go to large amps, 200 amps, 250, 500 amps. So what I do is, I connect batteries in series connection and in parallel connections. When I connect in series connections, if I, for example, I have 12 volt, for example, I have 12 volt 100 amp connected in series, the total output of this one will be equal to 12 plus 12 plus 12 plus 12. So the total is 400 volt staying current because they're in series. The same current goes through. If I connect them in parallel, if I connect the 4 in parallel, because voltage in parallel are equal, however the current, this terminal in here voltage will be 12 volt. This current is 400 amp hour. The system, 400 amp. I can take up to 400 amp out of it. The total current. That's why the 4 will become 12 volt, 400 amp hour capacity. If I connect in series and parallel to make a bigger thing, I can connect, let's say for example, I have 4 batteries, 12 volt batteries connected in series, then I have a 3 row of them. So this one, the first 4, this one is 48 volt, 100 amp hour. Then 48 volt, 100 amp hour. 48 volt, 100 amp hour. Then the total one, this system is 48 volt, 100 amp hour. And this one, 48 volt, 100 amp hour. The total system will be 48 volt, 100, 300 amp hour battery. So now I used 12 batteries. Each one of them has 12 volt, 100 amp. Connect them in series and parallel to form 48 volt, 300 amp hour system. That's how I can go. So now the system in here, my total power of this power bank, in here, maximum power is 48 times 300 amp hour. Will give me in watt hour the total battery capacity. Now, as an example, design a battery system to support the house consumption of 30 kilowatt hours using AGM. Like I said to you, I don't want to use this one. I want to keep it for now outside. No. How do you solve it? Perfect. What's the efficiency? I apply the equation straight away. Design a system, I have the AGM. So what I do now is, guys, P of the battery should be equal to 30 kilowatt hours divided the depth of discharge 0.5 times 0.95. So if you wanna get your calculator and divide this one, 30 divided by 0.5 divided by 0.95, it will give you 63.16. 63.157 kilowatt hours. Pay attention. Kilowatt hours, kilowatt hours. That's my voltage. Now, I have available batteries. Each batteries, guys, each battery is 12 times 250. The power of each battery, P of each battery, which is equal to 300. It's equal to 3,000 watt-hour kilowatt. So as you can see, how many batteries do I need? I need over 21 batteries. I need over 21. So I need number of batteries required is 63.157 divided by 3. This is kilowatt hours. So roughly, it's 21 point something. Now, so I need 21 batteries. Look, the available inverter, the available charger controller and inverters on the market, there's a 12 volt, 24 volt, 48 volt, 96 volt. So I need to stack my system, this 21, in parallel and series. But guess what? When I have in parallel, if I have 4 in parallel, I have to put 4. I cannot put 4 and a 3. No, it has to be the same voltage in parallel. So now I want to design a 48 volt system. 48 volt system. So I have four of them. Is that correct? 4 of them. So I have like this. Twelve volt. This will give me a total capacity of, this is the total capacity of 48 times 250, which gives me 12 kilowatt hours. So every 4 connected in series will give me 48 volt. I multiply it by 250 amps going through it, will give me 12 kilowatt. How many do I need of this? Divide by 12. I need 6 rows. I need 6 of this. So I need now 6. 1, 2, 3, 4, 5, and 6. This is my battery. This is each one of them. I have 6 times 48 volt. Each one of them is 250 mAh. So as you can see now, if I have a 48 volt system, I have 6 times 4. So I need 24 volt, 24 batteries. So now the total system for me is 24 batteries, not 21. Because if I have a 21, I can't. I end up either having less than this capacity. That's why I have to add the 3 extra batteries to be 24. So the total number of battery, it's equal to 6 times 4, it's equal to 24 batteries. So I need 24 batteries to design the system. If I want to design where I can take at a 50 DOD 30 kilowatt hours using 12 volt to 150 amp hour system. By the way, 30 kilowatt hour per day for a house in the Middle East, it's very high. In Dubai or the Gulf, because of the summer, because of the air conditioning, that's very low. Is that clear? Guys, during our introduction session, we will do way more examples. We spend about a good number of hours to do examples to educate ourselves in this domain. Instantaneous power. Guys, it's very important for us. The instantaneous power is the maximum peak power that can take for a certain period. So, because when I have a peak power, that means I have a peak current. When I have a peak current, my system will drop down. My voltage drop down, that means my operating hours, period, windows for my battery will get smaller. Let's do an example. Design the battery system to support the house consumptions for under these conditions. So what do I have? I have the same system. House current is 6 amp, and I'm using this. So what do I mean by 6 amp? Sorry. What do I mean by 6 amp? This is the maximum house maximum current. It's on. I have 230 volt at 6 amp. I need to make sure that at 48 volt, what will be the current? What will be the current at 48 volt? Because remember, let's use the same design. What will be the current? How do I do the current? This will be the same power. This will give me a power of this one. It's equal to 6 times 230. For this, here, the I will be equal to the power divided by the efficiency of the inversion multiplied by 48. So for the first power, 6 times 230, 6 multiplied by 230, 1, it's equal to 1.380 kilowatt. For this one, it's equal to 1.380 kilowatt divided by 0.95 multiplied by 48. Multiplied by the 48. Divide by 0.95, divide by 48, 30 amps. This will require for me, I will require 30 amps. I need it to run for 45 minutes. I need it to run for 45 minutes. Okay, I'll check. Hold on a second. Check 1 hour characteristic. If I take 100 amps out of it and allow it to discharge to this, I can run for 1.5 hours. If I have, this is under low, I'm talking about here 100 amps. Tells me that this battery is fully charged. If I take 100 amps out of it, can run for 1.5 hours. So yes, my system capable to provide 6 amp for 45 minutes. Because I'm only taking now 30 amps. Which is now, this under 30 amps, most likely this will give me about 5 hours. Most likely, could be less, could be more. So I need to make sure I check the data of my characteristics of my batteries to design my system. Is that clear? Where is the instantaneous current? So now the maximum current, I need to withdraw 30 amps for 45 minutes straight. Because I'm withdrawing 6 amp on the AC side. AC to 30 volt times 6 will give me the total power. I have to take into consideration the efficiency system. Like I said to you guys, during our introduction session, we will do way more solutions. Now, for a PV system, I need to make sure when I design, I have a PV solar system. When I design my battery system, I have to take this is my battery total capacity. This is my house daily energy consumption, the entire day for 24 hours, minus this is the house daily energy that's supplied directly from the sun. Because as you can see, I don't want to gold plate my batteries, my network. I don't want to design a very big battery that I'm not going to use. Costs a lot of money and doesn't last for long, maybe 5 years, 6 years, 7 years. So what I do is, I will get, hold on a second, I'll get the house maximum demand portfolio. Based on the house maximum demand portfolio, as I showed you in the previous lecture, I will get, this is the maximum house. How many kilowatt hours for the entire day? And then how many of this, what's the percent, how many kilowatt of this will be supplied directly from the sun? And then I divide it by the DOD and the efficiency to end up with the maximum battery size. Now, guys, this, I want you to know this information. When it comes to lead acid, you have a battery. You have 3 types of batteries. One battery that's designed for a low current discharge and lasts for a long time. Another battery is designed for high current, for a startup current, and the current for short period. This is known as a static current. They are not deep cycle ones. And there is the uninterrupted power supply battery, like a UPS system battery, suitable are not designed for frequent discharge and charge cycle. So if you have a device, you only want a high current for a startup, you have to go for these ones. These are not deep cycle ones, high current batteries. If you want a battery designed for high DOD with this type of deliver less peak current, you go for this type. If you want a UPS system, the uninterrupted, this type. So it's very important to know your activities. For example, if you are going to go for a UPS, if you have, for example, you're concerned about small change of power, for example, 10 minutes, 5 minutes, this type for your computers, for a critical power electronic system or electronic system, I go for this. This is very cheaper compared to the others. If I have a very high startup current, I just need a battery for a higher startup current, I search for this type of batteries. Now, you have, these are the most commonly used type. You have a lead acid battery, you have the AGM battery, you have the gel, and you have lithium ion. Safety precautions. I know what we spoke, it's a lot to comprehend, but remember, we're going to follow up with 2.5 hours worth of interactive session where we're going to go through step by step. All I need from you is to go listen to this lecture 1, 2, 3 times to make sure you comprehend it. So please, when I come back and ask a question, you should be able to answer me. Safety precautions. It's very important. What's a battery? Lead acid has a sulfuric acid. These could burn clothes, burn skin, damage eyes. So always when I deal with these ones, depending on the type, some of them are sealed, some of them are not sealed. I need to use one or protection must be one. And then battery terminal can deliver high current, as you can see, can deliver high current maybe for 1 minute. So all conductive items like ring, like watches, necklaces, when you work next to a terminal, please avoid having conductive material. The charging process, when you charging process of a battery, like I said, cause gases. These gases has a oxygen and hydrogen. Very flammable. Very flammable. That's why the battery must be put somewhere ventilated. You have to use an adequate ventilation system. If you don't use the ventilation system, you could cause major health risk issue for fire and more damage. Now, it's very important. Sometimes I go do an inspection and I see a lead acid, the old type. They have the water, all the gases goes up. On top of it, they have a relay. Guys, the relay, when it switches on and off, it spark. Switches that spark. Avoid this. Avoid it. Guys, this could cause major fire without you noticing. Connection and commissioning. Connection wires must be sized to withstand the maximum current. You have to be very careful and vigilant when you size a current 4 mil for an AC and a 4 mil on a DC. Because as we can see, the 6 amp in an AC equate to 30 amp in a DC. You have to be very careful about the sizing of the current. And also the voltage drop. The DC 48 volt voltage drop, if you drop 5 volt, that's a lot. You don't want to drop from your terminal of the batteries to your terminal of your charger controller. This voltage drop will reduce your operating time. Remember, the charger controller talks to the battery by reading the terminal voltage. Is that clear? So voltage drop, that's why sizing is very important. When connected in parallel series, it's important to pay attention on the polarity. When you connect in series, positive to negative, positive to negative. Connected in parallel, positive connected to positive, negative to negative. It's very important, guys, to make sure all the bolts are tight. There's no gap. Don't allow for a capacitors for anything to happen. Double check to make sure relay and switches are not installed in a close proximity, especially if it's not sealed one. Ventilation system is working. Sometimes maybe you put an exhaust fan, you put a cooling system, depending where are you located. Prior connection, test and check the voltage terminal. Before I connect my battery terminal to my inverter or charger controller, just get a voltmeter and test positive and negative. And also the voltage terminal. Determine the positive and negative polarity of the connection cable. After all safety precautions being done, go ahead and connect the inverter and the battery together and start doing the testing. When you do the test, make sure you have all the electric from an AC point of view, circuit breakers and safety switch like an RCD is in place. Maintenance. Depending on the type of the batteries, every single type of batteries, some batteries doesn't require maintenance or very minimum maintenance. Some batteries require high maintenance every 6 months, every year, every 3 months, depend on the data sheet. Please, whenever you do a job for your client, you install a electric system, photovoltaic, inverter, and a battery. Get a plastic sleeve, put it somewhere, and put inside the data sheet. So when someone comes back, can check what's been done, when is the last time, and all this information will be available to him. Please do this to help with the maintenance. It's also worth checking on the following. During hot day, if you have a very hot day, check your battery performance. If you try to reduce the current that you draw from the battery on a hot day, unless you provide a cooling system, for your batteries. Guys, if you have a car, and this car capable to take 1,000 kilograms, if you take 1,500, maybe it lasts a little bit. It can take 1,500, but it could cause a damage. If you have, for example, 1,500 kilograms you want to take in your car, what would you do? Would you take 1,500 and take the risk to break your car? Or you take 750 and a 750? Or maybe if you want to be more safer, you could take, if the road is not good, you could take 500, 3 trip. Here, the road, when it's no good, there's a big percentage to damage it, is the weather condition under heat or overcharge and discharge. That's why be vigilant about this element. Make sure the ventilation system is working well. Check the wire connection, make sure no loose end, and also check the sizing. If you take some of the wires, it could cause corrosion, depending on the connection. You connect the right terminals together. Connection wire must be sized to withstand the maximum current. And now, it is time to take a few minutes. We will take an example. Actually, I will post the example for you, because now it's been over almost 1.5 hours. I will post the example for you, so you guys can practice on. And during our next interactive session, when we do for solve problem, we will solve this example and additional one I'll prepare, and also I will answer any questions. I hope you will enjoy this session. I hope you enjoyed and you gained some valuable information about the batteries, and stay safe and see you next time.